So now we're gonna start with example 2. It says that suppose that the feasibility of packaging of fine wine in an oriented PET bottle with oxygen and sulfur dioxide permeabilities were 0.03 and 0.3 batter respectively. By the way, batter is a unit of pressure, but it is non-SI unit, and we're gonna convert it, as we're gonna see in the upcoming solution of the exercise, into the SI unit. All permeabilities are calculated in air at 25 degrees Celsius and a relative humidity 50% on the one side and 100% on the other. I'm writing the given as I am reading the question. If each bottle had a surface area of 720 centimeters square, a thickness of 0.046 centimeter, and holds 1 liter of wine, calculate the shelf life of the wine in the bottle, assuming that the bottles are perfectly sealed with gas impermeable screw cap closures. And the wine, we have the critical wine values are 5 ppm for oxygen, and when half of the free SO2, which means the critical value is 25 ppm, has permeated through the bottle wall. So, as I told you while I was reading, I was writing, this is the example 2. The given is that we have packaging of fine wine in an oriented PET bottles with oxygen, SO2, permeabilities. I wrote it here that they are calculated at the respective conditions. Each bottle has a surface area and the thickness is 0.046 centimeter. They hold 1 liter. We have to calculate the shelf life. The wines are perfectly sealed, and the critical point for oxygen 5 ppm, and for sulfur dioxide it is 25 ppm. So now we're gonna start in the first case for the oxygen ingress. We know that the concentration of oxygen in the atmosphere is 21%. So the atmospheric pressure is 21 atmospheric pressure. 21 atmospheric pressure. We need to convert from atmospheric pressure into centimeter SG mercury, which is the SI unit that we're going to work with in this equation. We multiply by a factor of 76. This is how we convert. So the pressure of oxygen would be initially 0.21 times 76, it's equal to 16 centimeter Hg. This is the first thing we have gotten from the given. Okay? Now, we assume that the vapor pressure, because they told us that it was hermetically sealed, it was perfectly sealed. So we're going to assume that the oxygen vapor pressure inside the bottle is 0. Oxygen vapor pressure inside bottle, we're gonna assume it is 0. Okay? The maximum quantity of oxygen that is able to be absorbed by the wine and still retain acceptable qualities, we're speaking about the critical oxygen value, it was said to be 5 ppm, right? Which is equal the same as 5 milligrams per liter. We need to convert it also to the SI units to perfectly work. 5 times 10 to the power minus 3 gram per liter. So we have 1 liter of wine, right? So per 1 liter of wine, as if we are saying simply, we can have and we can handle 5 times 10 to the power minus 3 gram of oxygen. Could be held inside or absorbed inside 1 liter of wine. Okay? So the first thing we did is that we convert the pressure of oxygen to the centimeter Hg. The second one is that we converted also the difference, let's say, in oxygen, the critical oxygen value, also to its SI units. We have the following equation, if we remember, okay, which is delta W that we work also with in the first exercise over delta T is equal with over P over X, A, P1 minus P2. Water vapor transmission rate, permeance coefficient, surface area, and delta P, which was the driving force. Now, when we are speaking specifically for gas, the equation shall be written as the following: Q over T equals P over X, A, P1 minus P2, or delta P. What is the Q? Q is the total amount of permeance that has passed through the plastic film. Okay? Total amount of permeance that has passed through the plastic film, or in other words, total amount of oxygen permissible. Total amount of oxygen permissible through the film. This is the Q. So Q is the total amount of permeance that has passed through the plastic film, or the total amount of oxygen permissible through the film. Okay. We have to take into consideration that the Q, the total amount of oxygen that is permissible through the film, or the total amount of permeance that has passed through the plastic film. If we recall that oxygen is absorbed differently, whether it is absorbed from an air medium or a water vapor medium, and it is much easier absorbed from an air medium, as we discussed inside the chapter. It is 32 times higher per unit volume of air than per unit volume of water. When we are speaking about per unit volume, so it is relative to the density. And therefore, when we are going to calculate Q, we have to calculate it with the permeance of oxygen per its density, per its respective density. So, by this, Q would be equal to the maximum quantity of oxygen that is handleable over the density of oxygen. Okay? The maximum quantity of oxygen that is handleable, and we have just calculated over here, 5 times 10 to the power minus 3, or let's say we have converted over the density of oxygen. Density of oxygen is 1, this is a standard value, 1.43 times 10 to the power minus 3 gram, and here we have gram per milliliter. Again, we calculated the maximum quantity of oxygen per the density of oxygen because the density is a very critical factor that we have to take actually into consideration. It depends, as we said before, whether it is inside an air or whether it is inside an water or whether it is in between, okay? Per unit volume, it is the permissibility per unit volume of something. It is about the density. So over here, we are calculating the Q factor, the maximum quantity of oxygen that is handleable per the density of the oxygen. The calculator would give us the following factor. 3.5 milliliter would be the permission ability of oxygen. Again, which is depending on the maximum quantity of oxygen per its density. And the maximum quantity of oxygen, it is already given. The second part, we're gonna continue it with the next video because 10 minutes for me is too much to continue as a single video. Keep on watching.